Alrighty, so in this video, we're going to work out some example problems for the loop analysis technique of analyzing circuits. Before, however, I get to those circuit examples, I did want to show you an interesting technique in how to solve a linear system of equations. By that, I mean things like two equations with two unknowns or things like that. This is called Cramer's rule. This is something you learn usually when you take a course in linear algebra or matrix mechanics. And it's a way of solving these equations, but instead of doing pure normal algebraic techniques like substitution method or things like that, we're going to use matrices and the way matrices work to try to more efficiently solve the equations. First thing, if you've never seen what a matrix looks like, a matrix is basically a way of writing some set of numbers that have some meaning in context with each other. And so here's an example. You know something called a scalar? And a scalar is basically like a number. You write 5 or 32 or whatever. A scalar, when we talk in math, it's basically a number. Then we learned about vectors. And a vector is something like the velocity vector tells you the components of the velocity in a certain direction. So you may have, 3i hat plus 4j hat. And that means the speed or the velocity of this object is 3 in the x direction and 4 in the y direction. And one way of writing it in a way that's a little bit more efficient, and the way a lot of engineers would write it, is something like this, 3 and 4. This is called a column vector, and it's basically a way of showing this vector, their components, but do it in a quick and easy way, nice and small. And so when you look at it, if you know what this is supposed to represent, you would say, okay, the top number is the x component of the vector, and the bottom number is the y component. And once you understand that, then we have ways of adding vectors. You would add the x components together, so that would be 1 in the x, and then the y components, 4 plus 1 is 5. And so you could do all sorts of quick addition and subtraction and things like this, operations on vectors, because we know how we're representing them. Well, a matrix is like the next level above that. Instead of having a single column, you have a set of columns. So you may have, A, B, C, and D. So it's like you have a column here and a column here, or a row here and a row here. Okay? But it's the same basic thing. In some way, these numbers relate to each other. We may not know how they relate right now, but depending on what it is we're doing, we would understand what this matrix represents. Now, matrices can be bigger than this. Of course, you could have A, B, C, D, E, F, G, H, I. This would be a 3 by 3 matrix. This is a 2 by 2. And you could have infinite matrices, whatever. But anyway, this is a matrix. It's a representation of something. Now, knowing this, when we get a system of equations, we may have something that looks like this. 2x plus y equals 4. And then minus x plus 3y is 5. Okay, and I may want to know, calculate x and y. Well, we know how to do this normally in the normal algebraic method. This is substitution. And so I would solve the first equation for y, let's say, plug that y into the second equation. Now I have a big equation for x, solve it, get a number for x. That's one of my answers. Take that x, put it back into the first equation, and now I can get the answer for y. However, what I'm going to show is the matrix representation of this equation. What this looks like, if I write it as a matrix, is I would say, first of all, note the coefficients in front of these variables. So I would make a matrix of the coefficients. I would say 2, 1, -1, and 3. Notice those are the coefficients of the variables. The x coefficients are the left column, the y coefficients are the right column. Next, what I would do is I would multiply this matrix times the vector x and y. And what would this equal? This would equal the answer vector, 4 and 5. So this system of equations, if I do this in terms of linear algebra, in terms of matrices, would be written like that. They mean the same thing. And I'm not going to go through this, but if you know how to multiply matrices or multiply vectors together, then we would do those techniques on this matrix equation, and we would get back to the original algebraic equations. But that's not the important thing. I just want to show you how you can represent these equations by the matrix representation. What I want to show you is, can you solve this using the matrices? That's what we're going to do. So let's take a general set of equations. Ax plus by equals c. And then dx plus ey equals f. And I want to be able to solve this using matrices. How do I do it? Well, first thing is make sure you have the original equations in standard form. And this is standard form. You have the x and the y stuff on the left side of the equation and a number answer on the right. Okay, so if you had something like this, let's say x plus 4y minus 3 equals 0, that's not standard form. You need x plus 4y equals 3. That's standard form. Okay, the x and the y stuff on the left, the numbers, the normal constants on the right. Once you have it in standard form, then what we're going to do is we're going to make 3 different matrices. How do I know there's 3? The reason I know there's 3 is because there's 2 unknowns. X is an unknown, something I want to calculate, and y is an unknown, something I want to calculate. The number of matrices you have to make is 1 more than the number of unknowns. So here I have 2 unknowns, so I need 3 matrices. What are the matrices? First matrix is called the W matrix. W stands for what's called Wronskian. It's a very special one. And it's really easy to make. How do you make it? You just take the coefficients that are in front of the unknowns. Exactly what I did at the top. So for this set of equations, the Wronskian is A, D, B, and E. Okay, so all I did was I took these coefficients and I made a matrix with them. X stuff on the left column, Y stuff on the right column. And that's it. That's the Wronskian. Then I'm going to have a matrix for the first unknown, call it the X matrix. Now, a lot of times, because I can't write in bold or italics or anything, to show that these are matrices, you put a little arrow. I mean, not an arrow, a little line on top. And that denotes this thing is a matrix. Just like you'd put an arrow if it's a vector. So the X matrix. What is the X matrix? The X matrix, and I'm going to do this in yellow, so yellow stuff for the X, is going to be just like the Wronskian, except since I'm making the X matrix, I don't use the X coefficients. So I'm going to use the Y. So I put those there, B and E. But now instead of the X stuff, I'm going to take the answers and put that where the X stuff would go. So C and F. Okay? So to make the X equation, the X matrix, I take the Wronskian, but instead of the X column having the X coefficients, I use the answer numbers instead. So notice B and E are the coefficients of Y. It's in the Wronskian and in the X, because that's fine. But where A and D were in the Wronskian, instead of using A and D, I use the answers to the equations, which is C and F here. The last one is whatever the other unknown is. In this case, it's Y. I'm going to make the Y matrix. And you could guess what's going to happen here. We're going to do just like the Wronskian. I'll do this in green, where I use the X variables, where the X stuff goes, A and D. But now, instead of using the Y variables, I use the answers, where the Y stuff would go. So C and F. Okay? So, all three of these matrices are very similar. The Wronskian, it's just the coefficients of the X and Y's, the unknowns coefficients. The X matrix is all the coefficients like the Wronskian, except instead of X coefficients, you use answers. And the Y matrix, just like the Wronskian, except instead of the Y stuff, you use the answers. Now, once this is set up, how do we actually use it? Okay, let's see. What you do is you say, if I want to calculate the X unknown variable, I want to know what X is equal to. Not the X matrix, but the actual answer to whatever X is. The way you do it is you're going to divide two things together. And I'm going to name them, and then I'm going to explain what these things are. To get the X, you take the what's called the determinant of the X matrix. And the symbology of that is like absolute value symbols for the X matrix. And you divide that thing, whatever it is, by the determinant of the W matrix, the Wronskian. Okay? Don't worry about what this means yet. And of course, if I want to do it for the Y, if I want to know the answer to Y, very similarly, I would take the determinant of the Y matrix divided by the Wronskian. And that would give me my two answers. So if I know how to do this, then quite easily I could get the answer to these equations. Now, how do we do this thing called a determinant? Determinant. It's really easy. Now, it depends on how big your matrices are. The 2 by 2 is easy to do. 3 by 3, a little more complicated. And then as we go bigger and bigger, it gets harder and harder. We're never going to have in our class one bigger than 3 by 3. So let's see, how do we do it? let's say you have a matrix A, B, C, and D. The determinant, which is straight lines, like an absolute value, the way you do it is this. You take whatever the A times D, A times D, minus C times B. Okay, so it's like cross multiply and subtract. Whatever the number A is times the number D, minus whatever the C is times the B. And that's it. That's your determinant. Very nice. Now what about 3 by 3? I'll show you 3 by 3 as well. This is a little more complicated, and there's actually many ways of doing this, depending on if you're an engineer, physicist, mathematician. I'll show you the physicist and the mathematician's way. Let's say I have A, B, C, D, E, F, G, H, I. And I want to take the determinant of this thing. All right, so just to make it clear, so I'm not, because generally speaking, when you do this, you get a whole bunch of lines everywhere and it makes it look messy. So I'm just going to draw them over and over again. First thing you do, A, B, C, D, E, F, G, H, I. Okay. First thing you do is you take first letter of the first line. So the first element, A. A. And then you're going to multiply it by something. What do you multiply it by? Well, if you take A, then you cross out everything in the same row as A and everything in the same column as A. And you're left with a little 2 by 2 thing. Guess what you do with it? Just what you did before. Cross multiply and subtract. Okay? So you take E times I minus H times F. Okay? So you start with A, cross out the row and column that A is in, and you're left with 4 terms. With those 4 terms, you do the little determinant thing. Then, let me rewrite it. A, B, C, D, E, F, G, H, I. Now that I'm done with A, I'm going to move on to B. So now I go to B. Again, I'm cross out everything in B's row and everything in B's column. Now, here's an important thing. You subtract B and you're going to multiply. This is very important, this minus here. It's not plus, it's minus. What do we do? Just like before. We're left with 4 terms, D, G, F, and I. We do the cross multiply and subtract business again. So it's going to be D times I minus G times F. And now we're done with that term. And as you can guess, we go to one more term, A, B, C, D, E, F, G, H, I. We take C now, the last one, cross out his row, cross out his column. What's left? D, H, and G, E. What do? We add C. So notice A, then minus B, then plus C. They alternate. So plus C, what do we have? D times H minus G times E. All right. And then with that, we're now done. These would all be numbers. You multiplying them out, add them all up, and you'll have your answer. So you can see the 3 by 3 is more complicated than the 2 by 2 because you have 3 different terms instead of just 1. But for each one, you're basically doing a little 2 by 2 determinant. Okay, so that's how we do a determinant. Now, let's actually take an example where we put all of this together. Remember, you're going to start with some series of equations, here they are here, where we want to know what's x and y. Because we need to know 2 unknowns, we're going to set up 3 different matrices. The Wronskian, the W, which is all the coefficients in front of the x's and y's. The x stuff goes on the left column, the y stuff goes on the right column. The next matrix is for the first unknown, in this case it's called x. How do you set it up? It's just like the Wronskian, except instead of the x column, we use the answers for these equations. But the y column is still there. And then the last matrix, it's for the second unknown, which in this case is called y. And he is just like the Wronskian, but instead of the y stuff, we use the answers. So, once you have these 3 matrices, how do you get your actual solutions, the x and y solutions? You do these determinants. Determinant of the x matrix divided by the determinant of the w gives you x. The determinant of the y matrix divided by the determinant of w gives you the answer to y. And once you're done that, you have your answers. So, let's do an example. Let's take, in fact, what are the numbers? I didn't write them down. Okay, let's take this example. X plus 2y equals 5, I think. And then let's take minus 2x plus y equals, let's make it 3y, I'm sorry. Minus 2x plus 3y is equal to 4. Okay. And what do I want? I want to find x and y. Okay. So, what's the first thing I do? First thing I do is I make my 3 matrices, because I have 2 unknowns, I make 3. The W is the coefficients of the unknowns. So 1 and minus 2 for x, 2 and 3 for y. Then I make the x matrix. So for the x column, instead of writing the x stuff, I write the answers, which are 5 and 4. The y columns, I use the y stuff, 2 and 3. And then the last one, y. For the x column, 1 and minus 2, I use the x stuff. And for the y column, instead of y stuff, I use the answers, 5 and 4. All right. Now that that's done, what do I want to do? I know I'm going to have to take the determinant of these things, so let's do it. Let's take the determinant of w first. All right, well, here's w, 1, 2, minus 2, 3. Take the determinant of that. So I cross multiply and subtract. So I have 1 times 3 minus negative 2 times 2. All right, so 1 times 3 is 3, minus negative 2 times negative 2 is negative 4. So 3 minus negative 4 is 1. So there's w. Now let's take the determinant of x. 5, 4, 2, 3. Again, cross multiply and subtract. 5 times 3 minus 4 times 2. 5 times 3 is 15, minus 4 times 2 is 8, so we get 7. Oh, I'm sorry. I just noticed something stupid here. Look, for the W, I said 3 minus negative 4 is 1. I don't know why in the world I said that. 3 minus negative 4 is 3 plus 4 is 7. Sorry about that. Hope you caught it when I did it, because I certainly didn't. All right, we got one more to do. Determinant of y. So what's y? 1, negative 2, 5, and 4. Again, cross and subtract. So we have 1 times 4 minus negative 2 times 5. 1 times 4 is 4, minus negative 2 times 5 is negative 10. 4 minus negative 10 is 4 plus 10, which is 14. All right, so all the hard work is done. We now have the determinants for all three. Now we can solve the problem. How do we calculate x? X is the determinant of the X matrix over the determinant of W. Well, we've already done them, so what's determinant of x? 7. Determinant of W? 7. So 7 over 7, which is 1. So x must be 1. What about y? What's the answer for y? Well, it's the determinant of y over the determinant of W. 14 over 7, which is 2. And we have our answer. So, here, we were given a system of equations. We wanted to find what's x and y, 2 equations, 2 unknowns. We could have done substitution, and maybe it would have been faster. But here's a secondary method. Either method will work. I'm not going to demand that you do one way or the other. If you like doing substitution method, go ahead and use that. If you like this method, it seems more interesting, go ahead and use this one. However you can do it, that's what you should do. Let's do one more example. This time we'll do the 3x3 version. Okay. Example. Let's take x plus 4y minus z equals, let's see, seven minus x plus 2y plus z minus 1, 2x plus y plus 2z equals 3. Okay, so I think this will work. And of course, what I'd like to do is find x, y, and z. Well, in order to do this, I have 3 unknowns, so I need to make 4 matrices. First matrix, W, is going to be all of the coefficients. So 1, minus 1, 2, 4, 2, 1, minus 1, 1, and 2. So these are just the coefficients of the unknowns. X in the left, y in the middle, z on the right. X matrix. Just like this, so 4, 2, 1 is the same, minus 1, 1, 2 is the same. But on the left, we will have, instead of the x column, we have the answers. 7, minus 1, and 3. For y, just like the W, so the x one stays the same, the z stays the same, but now instead of the y column, we have the answers. 7, minus 1, and 3. And the final one is z. just like the Wronskian, so this is the same, the y is the same, but now the z column is the answers. 7 minus 1, 3. All right, so we made our 4 matrices. Now, let's take the determinant. So we'll start with W. All right, so we have 1, 4, minus 1, minus 1, 2, 1, 2, 1, 2. So we start with the 1, and we cross out all of the 1 column and all of the 1 row, and we have 1 times. What do we have left? This little 2 by 2 on the bottom right, and so we do cross multiply and subtract. 2 times 2 minus 1 times 1. And now I'm done with the first element. So let me rewrite it. 1, 4, minus 1, minus 1, 2, 1, 2, 1, 2. Now I'm looking at the second element. I cross out his row and his column, and I have minus 4 times. What's left? These 4 elements. So I have negative 1 times 2 minus 2 times 1. Okay, again, cross and subtract. He's done. I'll rewrite him. We have 1, negative 1, 2. Take the third element, cross out his row and column, and what's left over? We have plus negative 1 times negative 1 times 1 minus 2 times 2. All right, so now that that's all written down, we could solve for this. What do we have? 2 times 2 is 4. Minus 1 times 1 is 1. So we have 1 times 4 minus 1. 4 minus 1 is 3. 3 times 1 is 3. Minus. All right, negative 1 times 2 is negative 2. Minus 2 times 1 is 2. So negative 2 minus 2 is negative 4. 4 times negative 4 is negative 16. Plus negative 1 times negative 1 times 1 is negative 1. Minus 2 times 2 is 4. So minus 1 minus 4 is minus 5. Minus 5 times negative 1 is positive 5. So 3 minus negative 16 is 19. 19 plus 5 is 24. Whew, W done. 24. Now we're going to move on to the X matrix. So the X matrix is 7, 1, or minus 1, 3, 4, 2, 1, negative 1, 1, 2. Let's just make sure that's correct. 7 minus 1, 3, 4, 2, 1, negative 1, 1, 2. All right. So we want to do the same thing here. Take the determinant. So I start with the 7 times 2 times 2 minus 1 times 1. Then I subtract the next term, which is 4, times negative 1 times 2 minus 3 times 1. Then I add the last term, which is negative 1 times negative 1 times 1 minus 3 times 2. Okay. So, what do we have? 7 times 4 minus 1 minus 4 times negative 2 minus 3 minus 1 times minus 1 minus 6. 4 minus 1 is 3. 3 times 7 is 21. Negative 2 minus 3 is minus 5 times negative 4 is plus 20. Minus 1 minus 6 is minus 7 times negative 1 is plus 7. So that's 41 plus 7, which is 48. Now we have the y. Let's see. This is going to be 7, negative 1, 3, negative 1, 1, and 2. And what's the first? 1 minus 1, 2. Yeah, okay. Same process. Start with the first element, 1 times. We have negative 1 times 2 minus 3 times 1. Minus, the next element is 7 times negative 1 times 2 minus 2 times 1. Plus, the last element, negative 1 times minus 1 times 3 minus 2 times negative 1. What does this equal? 1 times. Minus 1 times 2 is minus 2. 3 times 1 is 3, so minus 3. Minus 7 times. Minus 1 times 2 is minus 2. Minus 2 times 1 is minus 2. Then we have minus 1 times minus 3 plus 2. Minus 2 minus 3 is minus 5 times 1 is minus 5. Minus 2 minus 2 is minus 4. Minus 4 times minus 7 is plus 28. Minus 3 plus 2 is minus 1. Minus 1 times minus 1 is plus 1. 28 plus 1 is 29. Minus 5 is 24. So now we have y done. One more to go. All right, so our last determinant, z, is going to be 1 minus 1, 2, 4, 2, 1, 7 minus 1, 3. And now we need the determinant of this guy. Same as before. Start with the first element, 1 times 2 times 3 minus 1 times negative 1. Minus the second element, which is 4, times minus 1 times 3 minus 2 times negative 1, plus the last element, which is 7, times negative 1 times 1 minus 2 times 2. All right, so we have 1 times 2 times 3 is 6, minus 1 times minus 1 is plus 1. Minus 4 times minus 1 times 3 is minus 3. Minus 2 times minus 1 is plus 2. We have plus 7 times, negative 1 times 1 is negative 1. minus 2 times 2, which is minus 4. 6 plus 1 is 7, times 1 is 7. Negative 3 plus 2 is negative 1, times negative 4 is plus 4. Negative 1 minus 4 is negative 5, times 7 is negative 35. Right, 7 plus 4 is 11, minus 35 is 24. Negative 24. All right, so we've now done all the hard work. That's all finished. Let me write down what the answers were. We have a W, we have an X, we have a Y, and we have a Z. Let's see what they were. The Z, of course, I have right here is negative 24. The Y was 24, the X was 48, and the W was 24. All right, so now we can get our answers. X, determinant of X over determinant of W. 48 over 24, which is 2. Y, determinant of Y over determinant of W. 24 over 24, which is 1. And lastly, Z. Oops. Determinant of Z over the determinant of W. Negative 24 over 24, which is negative 1. And we have our 3 answers. So there you go. That's as hard as this is going to get. 3 by 3 matrix, 3 unknowns, 3 equations. This is how you would do it. The technique is the same. You start with your equations. You make your matrices with them. Once you have your matrices, do your determinants for each one. We did it for W, we did it for X, Y, and Z, and we got all of our answers there. Once you have your answers, you could get the solution by doing the ratio of the determinants, as we did here. Obviously, this looks very complicated, especially if you've never done determinants before. 3 by 3 determinant is pretty tedious. Each individual step is fairly easy, especially when you've gotten the hang of doing this little, cross out the row and column, and then you do the cross, multiply, and subtract. But after you've done it a few times, you get used to it. There's another way of doing this that engineers tend to use, but it's actually more complicated to see it that way than to do it this way. This way is the best way to do it, because trying to do it the other way involves graphically trying to write things in certain positions, and if they're not in the right positions, then it's hard to see things clearly. This method, which is the physics method and the math method, you just follow the rules, and the rules give you the numbers. The 2 by 2 matrix, of course, is very easy. It's just a single one of the cross, multiply, and subtracts. And most of the questions you get here are going to be like that. You may get some that are 3 by 3. And in fact, if you get some that are 3 by 3, if any of these numbers are 0, then it actually gets very quick because half the terms drop out. Here I just decided to do an example that's as complicated as it can possibly be, so you can see how the hard ones are done. Ones that you may get on a test or something would probably be easier. And at the end of the day, it's optional to do it this way. If you'd rather take this original set of equations and just do the normal algebraic substitution way, go ahead and do it that way. That's fine. I tend to like doing the matrix version just because it feels like a puzzle. It feels a little more fun to use a higher technique than to just write out a whole bunch of substitutions. But anyway, for this video, that's all I'm going to do. I'm going to do a second video where I use this information to actually solve some of the circuits. But I wanted to show you this in case you're interested, because a lot of times doing loop analysis will give rise to a system of equations that you have to solve, and I wanted to give you a new tool to be able to use, if you like it, on how to solve them. If you don't like this, or you're afraid it's going to be too complicated or you might mess up, feel free to use the old substitution method. That's fine with me. But look out for the next video, which will have particular examples of the circuits. See you then.